Welcome back, everyone. Firstly, thank you everyone who's given feedback, especially on the compression side of things with the audio and image quality. Trying some new things out, including a new mic and post-processing stuff. So thank you for the feedback, and I hope that with the feedback, I can continue to improve and give back to the community that has given so much to me and many others I know. Um, so with that side note out the way, now let's get back into quantum mechanics. By the end of this video, you will be able to dissect what it means to be a canonical commutation relation and what observables are compatible and incompatible, and therefore what results we can derive from them. Check the description because there's a lot of other details about how I set this problem up that I just don't want to include in a video because it'll clog it all down. But there's a free PDF that you can download and look at your own discretion and desire. Um, but without further ado, let's get into this question. For part A, what we want to do is work out all of the canonical commutation relations for the components of the operators R and P. And in this case, what we have to recall is that R and P are variables in 3 dimensions, or vectors in 3 dimensions. So R is the position vector and P is the momentum vector. And that'll come into play in a little while. And so what we're looking for is ordered pairs of things like XY, XPY, and so on. Now for part B, we want to confirm the 3-dimensional versions of Ehrenfest's theorem. There goes that famous theorem again, where we have the time derivative of position leads to momentum with the 1 over m factor, and the time derivative of momentum leads to the what we call the negative gradient of v, so the negative derivative. In this case, we just extrapolated that to 3 dimensions. And C, we want to formulate the Heisenberg uncertainty principle in 3 dimensions. This whole chapter is predicated on bringing us out to 3 dimensions, whereas in chapter 1 and 2, we simply worked on 1-dimensional cases. We brought the formalism together in chapter 3 so that we can extrapolate our results into the several other dimensions. And if you're really crazy, you can go into even further dimensions, but that's for another class. So now we'll go ahead and move on. Okay, first and foremost, being in 3 dimensions means that we have a lot of different pairings of variables. And so what the author gives us is the notation I and J for the indices, and to me that's just a bad notation with I being the imaginary unit as well. But also it just becomes cumbersome because the bases we're working in is X, Y, Z, or we could be R, theta, phi, whatever other things else. So I understand why we want to generalize the indice rule. However, there's a lot of background to the setup of this thing. That way we know what kind of index pairs we need, and more specifically, how we can condense the pairing needed based on the type of operators and what their relationships are. Um, Also note that things like the commutation relations have properties such as anti-symmetry, which is where we switch the indices and we get a negative sign, things like that. All of that is in the PDF that you're more than welcome to view. But I do this just to forewarn you that we're going to have a lot of things come up like this, so having an appropriate setup strategy saves you a lot of time later. Okay, so in part A then, we're looking at the position-position commutation relations. And what we can tell by this is that because we're the same operator, position and position, we know that anytime the indices match, we know that we have the commutator of the same operator in the same base. So therefore, we know that the commutator of the same thing is 0. So that's how we end up with the 0 diagonal, as we see in the indice pair needed table or matrix. Again, the anti-symmetry comes in, and we see that we could flip the order of x, y, and y, z, and at the cost of a negative sign. Again, refer to the for the PDF for more detail on that. The whole point of that is to highlight that we've now reduced the potential 9 combinations of x, y, and z down into 3. And so this is why I think the setup is so important to get down first. For all of the collective pairs of the commutators for position and position, we have boiled it down using properties to just needing to find the xy, xz, and yz. Again, all those properties are listed as to y. But now that we use those properties and we have this set up like this, we can calculate 3 things instead of 9. Saves us a lot of time, and this is where insights into linear algebra come in again, so just be prepared to the fact that this will be used over and over quite soon. Now that we understand the scope of what we need to do for this particular commutation set of relations, we can quickly calculate those with the commutator brackets. Again, in the PDF, I have acting on a test function just to keep it consistent with the fact that these are operators, but no big deal here because the position operators are just the variables themselves. And in general, if you have the same kind of operator, like position, position, regardless of index, you should be all right with this. It just becomes messy with the test function, as we'll see in the momentum case. But nonetheless, the position operators are just the variables themselves, so all we have to do is realize that we could switch these two and we get a 0 for x, y, and similarly for the other ordinate pairs. And so recompiling this, again, if we look at this little curly bracket matrix, that's just a collection or a set of the other indice pairs. And we see that we have zeros across the board for all of them. So what we can conclude is that the commutation relation for any pair of position operators, regardless of I and j, that equals 0 for all of them, as indicated here. And again, with this kind of setup, it becomes really easy to kind of fast forward this process. This 0 part here should come as no surprise really after what we saw in chapter 2, and especially in chapter 3, reference compatible versus incompatible observables and what's needed for the uncertainty relationship. But nonetheless, we can now streamline this to the momentum-momentum commutation relations. And again, we see that momentum-momentum is the same type of operator, so the main diagonal is 0. So that saves us one thing. The other thing we notice is that antisymmetry allows us to switch the pairs here. So again, all we need to do is find 3 of the coordinates or pairings here, and we'll be good to go. Alrighty, momentum and momentum. If we look at the fact that we had an XY pairing that we needed, the leftmost being the X, the rightmost being the Y, we've kind of seen this before, but now we can break it down into a little more work or a little more usefulness. Here, we know that we're going to have to set up this by definition a commutator relation, no big deal there. But remember that now once we have this, these operators were defined as h bar I or negative I h bar times their partial with that respective direction or variable. So x for x, y with y, move it on through, you see what we're dealing with. Alright, but nonetheless, we see that we get d by dx, d by dy. Again, you could operate this on a test function. You don't really need to for the sake of we have a fundamental theorem from calculus that allows us to switch the order of the derivatives with no problem. Notice here that we have a factor of h bar and I in all of these, so we could square them and factor them. No big deal. What I'd like to point your attention to now is that on the left-hand side of this, we have a dx and then dy highlighted here. On the right-hand side of the minus sign, we have a y and x, as we see here. And Clairaut's theorem allows us to switch the order of those derivatives. Thus, what we see is that we have, when of course we evaluate that I to -1, we have a minus derivative here with a plus derivative here, and thus we get a 0 for that commutation relation. Again, you could test this on a function, no big deal, but the fact that we're allowed to switch the partials due to Clairaut's theorem saves us a huge headache. And so naturally, by extension, we could see that xz and yz lead to the same 0 thing, so not too bad there. I think we're starting to catch the drift of these relations. As promised, here is the YZ, same thing. Again, the PDF has all of the cases and all of the work. It's a lot of rinse and repeat, so to speak. But now, bringing it all back to what we started with, we realize that the commutation relation of 2 of these observables, rather operators, for the momentum sense, they're the same type, regardless of what their index is, they equal 0. So everything, when we're dealing with the same type of operator, it can, as you see, is starting to generalize to 3 dimensions that the same type, regardless of index, is going to equal 0. And that is good to know for us because we can start to classify these things and highlight them for when we need these properties again. As you see, the properties of the commutator brackets that we covered in Chapter 3 are already coming to a very helpful insight. So be aware, the properties are not meant for you just to memorize them, whatever. They're there to help you for bigger problems like this and to give you a general landscape view of what's going on. Now, this is going to be fun moving on to the position-momentum commutation relations. Okay, we could also find a momentum position, but that is just the anti-symmetry rule, which we already have baked into the indice pairs needed here. And what we can, since these are not the same type of operator, we can't just put zeros for the main diagonal. We have to have the case where we see the XX, because these represent the X position and the X momentum. And so here we see that we need a highlight of 6 pairs needed: XX, YY, ZZ, XY, XZ, YZ, and all of these 6 are much easier to compare using something like this than it would be having to make another table or try to guess which ones you need. Alright, enough of me rambling. Let's see what the XX case looks like. Here you will need a test function, so just go ahead and get used to that setup again. And you see we applied the definition of the commutator bracket, and then we plug in the definition of the momentum. Pretty straightforward, I would say. We've seen this before in Chapter 1, I think. Definitely Chapter 2 when we showcased the XY or the X and P commutator before. So let's go ahead and finish up with this one. We see here that both of them have an h bar of I factored out, no big deal. We do have to right distribute the f into this thing because that right distribute gives us a product rule here for the derivative. Highlight it in this bracket here. Again, we've kind of seen this before, no biggie. So what we see here is that now once the product rule is applied and we distribute the negative sign to the f and to the x df dx, we see that the product of x and df dx cancel due to the minus sign. We're left with the leftover fact of negative x, or negative f rather. So the negative comes through. Again, all expected. Since we started with the test function, we can cancel out the test functions on both sides of this equal sign. And note that we can compact this down to an I by rationalizing that denominator at the cost of a negative sign. So we can conclude that the commutator for the x operator and the momentum operator in the x direction is IH bar. Again, we've seen this done in other chapters, so we can streamline through that. As you'd imagine, the other two on the diagonal are the same thing. The work is shown in the PDF as stated here. So now we can move on to the cross terms or the cross pairing. This is where the fun begins. Here we see that plug in definitions straight across, factor out that h bar I, and then we're left with a product rule again. Apply the product rule, except this time the derivative on the x, right, since it's not with respect to x, it goes to 0. It's with respect to y. And this 0 term multiplied by the f term gives us a 0. So what we're left with is a 0 as a whole, and then distribute the negative from this right here onto this product. And again, that cancels, so we're left with a giant 0 in this test function bracket. So what we can conclude is that we have the x hat and the y momentum equals 0. That is nice to know. And this gives us insight into other things too. We'll see that in due time. So similarly, as you see, the other cross pairs are going to have a similar problem with that partial derivative. So we just fast forward through. We get a 0 here and a 0 here. And I think that the way I set this up with the kind of matrix table, hesitant to call it a matrix, so it's not really extrapolated to one, it's just a collection of things. Here, I want to highlight what we can see as far as a characteristic of what these operators do as we extend dimensions. Here we see in the blue column and rows that we have zeros lining up because cross pairs cancel to 0. And we're left with a main diagonal here of all IH bars. What this can highlight extensively is the fact that this looks like, once I factor out the IH bar, I'm only left with pairs that are the same indice. So X and X, Y and Y, Z and Z. highlights perfectly the use of the Dirac delta or the Kronecker delta, which tells us that we're 1 for anything that is indice matching and 0 for anything that is not indice matching. This is kind of hard to see unless you set up something like this, but it can easily be shown however you want to do it is best for you. But for me, this highlights extensively the use and compactness of this nice little compact Dirac delta function. Again, sometimes it's good to see what these things are actually asking us to do. So that completes our round 1 of commutator relations. Now let's see how we can apply some of these things. So finally then, on to part B. In part B, we still had to use the generalized Ehrenfest theorem, and we've kind of become comfortable with this theorem with how much it's used recently in the theory. What we can now conclude though, or rather what we can go ahead and highlight, is that we can use the old results that we've had and fast forward this process. Here, if we're trying to show that it holds in 3 dimensions for R, for Q being R, we can start with the one-dimensional case of X and then extrapolate that on. Here, what we see is that Q being X, we plug everything in. Again, X, the operator itself, is not dedicated to position, or time rather. It is just the position function. So if I just look at the time derivative of X, that goes to 0. No big deal. Multivariable calculus takes care of all that. Again, the only one that really has something to deal with operator-wise is the harmonic oscillator potential. That is time dependent. So until we see that, this can just be assumed 0 until verified needed. But nonetheless, what we have to do is be careful of this pesky p squared here from the Hamiltonian. This p squared, if you go look in the chapter notes, is actually equal to the square of x, y, z added together. And that's pretty typical what we've seen in the language of vectors before, since this was the momentum vector, and if we square it, then we see that we get the x squared, y squared, z squared. It looks like the dot product, so keep that in mind. The inner product for vectors looks like this. This is what we deal with. The hard part now is to be able to understand what to do with these squares, and thanks to other properties that we've seen before, we can narrow down this commutator relation using things like linearity, and distributivity, Also here, let's note that the V from the potential energy term and X, that goes to 0 because both are a scalar in this sense, or rather, both are a scalar or constant in this sense. So we see that they can commute with one another and they go to 0. Again, all those things are properties we've shown in chapter 3. I'll link some more below. But nonetheless, let's go ahead and evaluate this p squared commutator bracket. Alright, so as promised, line 1 here, we have to use linearity to split up the plus signs. And then I'm only going to highlight in the video how the distributivity law works on the x, because the other ones cancel to 0, as highlighted in red and green, as you'll see why here. When we use the distributivity, can't speak today, when we use that law, what we see is that we get a commutator with px and x and a commutator with px and x. That's nothing new. But we would end up with a commutator pyx and a pzx, and we've shown in the last part of part A, those go to 0. So that's again why we can go ahead and relate those matrix tables to these and simplify down very quickly. Nonetheless, what we also showed is that px and x is just the inverse because of anti-symmetry of the h bar over I. Negative, so 2 negatives make us a positive, and we could just substitute in an h bar I, and then again we see we have the same thing on both sides. So let's go ahead and tidy it up. We see that we get 2 copies of 2 copies of h bar I and px, no big deal. We know that in the expectation value, it being a integral itself, it's linear, so we can take the 2 h bar I out, which we see here. And that cancels wonderfully with the fact that we have I and h bar times 2 on the outside from this. Easy peasy. We see that we now finalize down to the expectation of px and m over m. And similarly, this holds for the y and z case as well. So we can conclude that the time derivative of the position vector in the expectation is equal to the momentum expectation over m. We love to see how this thing comes together once again. Again, the PDF has the rest, so we'll move on to part C then. Or rather, the next part of part B, excuse me. What this says is that now we need to test for the other part or the other pairing of Ehrenfest's theorem, which is the momentum. This was one of the big ones that we had from chapter 1. I believe it was 1.17, something to that effect. I'll link it below because I like relinking. Here though, if we're taking the one-dimensional case again, just to highlight the properties, what we see is that if we plug in the momentum in the x direction, we see that we're going to have to deal with this px again, or the p squared again with the px. Again, the px operator is just h bar over I d by dx. That has no time relation to it, so it goes to 0. Again, split it up by linearity, no big deal. This right here, we actually found in a previous problem. I can't remember which one right off the bat. I don't think it was 3.14. Again, I'll link it below. But old results being used saves time, so we see that commutator bracket goes to this, and we could save time there. Again, split these up, use linearity. What I'd like to show is that knowing that we had to distribute last time, we see that we end up with the same type of operators inside those distributed commutator brackets. And since we have px and px, py, px, and repeat to z, all of those go to 0. All those evaluate to 0. So we get a nice 0, 0, 0 here. Again, rest of the work's in the PDF, but all those zeros go down and cancel out so nicely to the fact that we're left with this negative h bar I d by dx of v, because we put the I underneath for the sake of simplifying. And so here we see that, again, expectation values are linear. We can cancel out the fraction out front with the fraction inside, and we're left exactly with what we expected to have, negative dv dx. Of course, we can extrapolate this to the y and z as well. So let's see how we can conclude this theorem. Knowing that these extrapolate down, we see that the time derivative of the momentum expectation, three-dimensional vector there, is equal to the negative gradient v. So this is exactly what we're looking to have. Perfect. Moving on to part C, we'll go through this really quickly because I think we see what we need. Heisenberg tells us that we need the operators to be the position and the momentum. That's the Heisenberg view of uncertainty. Of course, there's other uncertainty relationships that we just don't really need because of what type of observables they have. Nonetheless, for Heisenberg, we need to let A equal R, again, index out, B equal P, index out. And so if we're looking for this generalized form from the generalized uncertainty principle, let's go ahead and plug in. We saw that the generalized form for the commutator of any of the position and any of the momentums was equal to I h bar delta. Cool, we like that, no big deal. So what we see is that the i's cancel, thanks to linearity again, and we're left with an h bar over 2 with the Dirac delta in it, ij of course, again, chronic, I can't speak. Anyways, this delta term goes to 1 when we square it, so it's no big deal. So we see that the left-hand side with the uncertainties, the standard deviations squared gives us the variance. We need the standard deviation, so take the squares out. We see that this now becomes a cancellation of square here, cancellation of square here, and we're left with the uncertainty of Ri and the uncertainty of Pj is greater than h bar over 2 for the Dirac Kronecker delta of Ij. It's Kronecker delta, not Dirac delta. But Kronecker delta here, and so we see that we need to evaluate this for all of the indice pairs, and all the indice pairs that we have in this x, y, z basis are labeled here. Again, a matrix just makes this convenient. So let's see how we evaluate this generalized statement for all of these ordered pairs. So we plug them in. We see that we have a collection of things. We have the ordered pair of x and x up top, yx, zx, and so on and so forth. But we know that the Kronecker delta gives us a 1 when they match and a 0 when they don't. So easy enough to figure out. The only thing that survives is the main diagonal, and so we have our relationship shown perfectly as we expected. XX gives us h bar over 2, yy h bar over 2, and zz over h bar over 2. Wonderful, wonderful, wonderful. We love this stuff every time, all the time. Again, there's a lot more to be said about this, which you can check out later. But what is very important to notice is that setting things up like this saves a lot of time. And regardless of my rambling about it, what we can say is that if you can set up things like these in a matrix and understand what the matrix forms are telling us, are we triangular, are we symmetric, yada yada yada, that saves us a lot of a lot of pen and paper time later. So let's go ahead and be thankful for the linear algebra folks and the quantum mechanics folks before us, because we can now understand what the new math is telling us. And I will see you at the next one. As always, thanks for listening to me ramble. I hope you enjoy this stuff as much as I do, and I can't wait to, help everyone learn because this stuff is so much fun. And yeah, we'll see you next round. Happy learning.